So the last real short section is on catalysis. So catalysis is when you add something to a reaction that is not a reactant or a product, or doesn't appear to be a reactant or a product, but speeds up the reaction. So it doesn't change the reactant or products, but it changes the reaction to make it faster. So what they usually say is a catalyst is something that speeds up the reaction and is not consumed. Okay, so let's look a little bit more into this. Here's a sort of a classic reaction that we catalyze. It's hydrogen peroxide decomposition, right, with a catalyst, in this case iron chloride, or manganese dioxide. There are a number of substances that work to decompose hydrogen peroxide, but if it's in the same phase, okay, reactant in the same phase as the catalyst, we call that a homogeneous catalyst because it's part of the solution, right? Remember, if you make a solution and it mixes uniformly, then we call that homogeneous, right? So that would be a homogeneous catalyst. And then you can also have surface-based catalysts where the reaction has to take place on the surface, but there's something about the surface that makes the reaction more facile, makes it go faster, okay? So heterogeneous catalysts are reactants in a different phase than the catalyst. Now, in general, what we say is catalysts are unchanged by the reaction, but they're actually involved in the reaction. Otherwise, they couldn't do what they need to do. And so I'll show you a couple of examples in how this works. Oftentimes, though, because it's not really a reactant or a product, the catalyst gets written above the reaction arrow. Now, in a reaction mechanism, if you're using a catalyst, then the catalyst becomes part of the elementary steps. But in the end, usually it cancels out. And so it's not apparent in the overall reaction because not only does it get used at the beginning, but gets produced back at the end or during the reaction, gets reproduced, so it looks like it never got used. So how does a catalyst change the mechanism? Well, that's complicated. There's a number of ways in which you can change the mechanism. But overall, it lowers the activation energy either by modifying an existing step or altogether adding a different step that ends up in the intermediate producing a completely different reaction. Okay, or sorry, completely different reaction, but then it yields the same product. So in this case, this is for bromide catalysis of the reaction. The bromide actually leads to a set of products and intermediates, which then produced the final products of the overall reaction. Overall, if you take these reactions and add them together, you still get, H2O2 makes H2O and oxygen gas. But again, it can lower, all it has to do is lower the activation energy. It does not have to add a step like this. It could just bring the top of the hill down by making the reaction conditions more favorable for the reaction in some other means. Now, if you have a heterogeneous catalyst, I wanted to show you this short video because heterogeneous catalysts are what you see, for example, in a catalytic converter. And a lot of industrial processes use heterogeneous catalysts. The reason is when you have a solid phased catalyst, you don't have to worry about removing it from the product. It's basically never like in solution with the product. And so it's easy sort of just to flush the reactants over it and get a very high rate of reaction. And then the catalyst, because it's heterogeneous, right, stays in one place.
In a platinum-based catalytic converter, nitrogen monoxide molecules in the exhaust stick to the surface of the platinum. The molecule decomposes, each atom remaining on the surface. When another NO molecule comes to the area, it also decomposes, and its N atom bonds with the other N atom on the platinum surface. The O atoms also combine. The gaseous nitrogen and oxygen molecules then float away from the surface.
So in reality, right, this is a process called chemisorption, right? That's why I put that word there. I don't know that it's in your textbook. Chemisorption occurs. There's usually some active site on the catalyst surface. The molecule will literally sit, right, on the surface, and then the individual atoms of the molecule have a preference to be bonded to the platinum catalyst rather than to each other. And at that point, you have free atoms sort of diffusing along a surface of the catalytic converter. When they run into another atom of the same type, right, that interaction creates a situation where the molecule is no longer attracted to the surface, and then it diffuses away, opening up the active site for the reaction of the next pair of molecules. So in a sense, like one of the methods in which catalysts work is by optimizing the conditions, right, where the two reactants can be held together for a long period of time on the surface of the catalyst, for example, and that actually helps to speed up the reaction. Now, you know how we talked about that could have happened in the gas phase, for example, right? But you know how we talked about in collision frequencies, two molecules have to collide for a product to be formed. Well, one of the roles of a catalyst is often to create the parts of the molecule that are needed for the reaction so that when the second molecule comes in, it's being held in place. It's able to react more efficiently that way, okay? Because it's being held in place and ready to react.
In a platinum-based...
Okay. I'll skip this one. Enzyme kinetics, just a little, again, another example of catalysts. Enzymes are biological catalysts. And so in the terminology of biochemistry, you have a substrate and you have an enzyme, okay? And the substrate has a shape that fits the enzyme. So what happens in a lot of catalysts is the enzyme locks in, right, to the substrate. And you could think of it like a lock and a key, but it's not really rigid like that. So what happens is the substrate comes in, and then they sort of do this little bit of like getting comfortable thing where they change their conformation a little bit to become more tightly bound. So the pocket is really flexible. You have to remember it's just a bunch of bonds of molecules, and the bonds can rotate and things like that. So it gets comfortable in that position, and oftentimes in those enzyme pockets, there's a position for either another cofactor that causes the reaction to happen, or sometimes there's just an amino acid, for example, that is acidified, and that hydrogen is needed for the reaction. So it sort of creates a situation where one of the reactants for a reaction is held in place when the molecule attaches to it. So once the enzyme does its business, right, and creates a reaction, the bond, there's often something that's cleaved in the substrate molecule. Once that's been broken, the shape is not the same anymore, and so it releases from the pocket of the enzyme, and it's available for another cycle of the reaction. Sometimes something is needed to sort of regenerate that, some energy is needed or something like that, but that's the idea. Substrate comes in, gets into the pocket, a reaction takes place. After the reaction takes place, this enzyme substrate complex doesn't fit like it did before, and so the substrate leaves, right? But it's actually leaving as the product molecules instead of the substrate now. Well, that kind of covers it for the second half. It's a large half of the kinetics chapters, and feel free to shoot me a message if you have any questions.